Section 4.1a, Radian in degree measure. And this is the first section of trigonometry. Now, you've probably done a little bit of trigonometry in Algebra 2, so it's nothing completely foreign to you, but we will be going into a lot more detail in trigonometry for the rest of the year. Now, trigonometry is important for its own sake and has many applications in engineering, but it's also important because so much of calculus depends on it. So um, the most important part of the course is, as I've told you before, the second semester, because we talk about functions in chapters 1 and 2, and we talk about trig in chapters 4, 5, and 6. But the most important part of the second semester is what we're starting now, and that is the trig part. First, a little bit of review. You might look at this screen and say, "Duh," maybe this is all review for you, and it's something that it's already part of your memory. But it's still worthwhile to go through it because sometimes we can forget which quadrant is which, and what an initial side and a terminal side is, and what standard position means. So that's why we're going through this today. Now the Roman numerals represent the quadrant numbers, so quadrant 1, and then going counterclockwise from quadrant 1, we have quadrant 2, quadrant 3, and quadrant 4. The initial side is on the positive x-axis, and the terminal side is in various places in the different quadrants. So this would be an angle in standard position, and the pink arrow here indicates the magnitude of the angle. Reviewing positive angles and negative angles. So positive angles go counterclockwise and negative angles go clockwise from the positive x-axis, which is the initial side. Coterminal angles, that just means that the terminal sides coincide, and so we have angle alpha, and that angle alpha it has a terminal side in the third quadrant, and this angle beta, which would be a negative angle, has a terminal side in the third quadrant, and so these two angles, alpha and beta, would be considered coterminal angles. The same is true over here. In this case, as you can see, both angles are going counterclockwise, so they're positive angles. But angle beta goes all the way around and then ends up with its terminal side in the same place as angle alpha. These are also coterminal angles. All right, so here is where we get into something very important. You may or may not have seen this before, but even if you have, it's very important to understand what a radian is. Okay, up until now, most of our work has been done in degrees. Degrees are what we're used to, especially in this country, because it's our system. We talk about 180-degree turns. We talk about doing a 360 slam dunk. We talk in degrees and we think in degrees. This is what we're used to. In the same way we talk about feet and inches and pounds, because that's what we're used to. All right, but I think after today you're going to see why radians are actually a better measure of angle. And the other reason we're learning radians is because, yet again, calculus depends on it. You're going to see radians a lot next year, and you're going to see them a lot during the rest of this year too. So what is a radian? All right, a radian is, by definition, the angle when arc length equals radius. All right, there are many different ways that you can express that, but the most important thing for you to do on this screen is to observe this little pi wedge and understand it. Okay, so for this little pi wedge of radius r, the arc length s is arc length, the arc length s is equal to the radius r. And no matter what circle you have, no matter how small or big your circle is, when you have such a pi wedge for which radius equals arc length, the angle it makes will always be 1 radian. 1 radian. Now this is what a radian is by definition. You could compare that to the metric system. You know, the metric system is really based on 1 gram of water, where 1 gram of water is equivalent to 1 cubic centimeter of water. So what we do is we relate mass to volume, and therefore we have you know, a logical basis for a system of measurement. Well, the same is true of radians. Okay, the same is true of radians. With radians, we're relating radius to arc length in a way that degrees don't even attempt to do. And therefore, even just based on pure logic, a radian is really the most logical unit of angle. It's the most logical unit of angle. All right, so make sure you understand what a radian is by looking at this screen and this pi wedge. And when you feel confident that you understand what a radian is, that it is, there is 1 radian when radius equals arc length. At that point, then you can proceed on to the next screen. All right, so this is a little graph that shows us a full circle with the different pi wedges. And these pi wedges are each 1 radian pi wedges. And if anyone wants to celebrate a little bit when we do Pi Day, you know, we're going to do Pi Day on March 14th. And March 14th, because it's 3.14, you know, 314, 3.14159 is pi. Well, when we do Pi Day, you're certainly welcome to bring in a pi and cut it into this number of radians. All right, but we'll talk about that more in class. Let's look at this diagram and make sure we understand it perfectly. Okay, so follow the mouse arrow, and what I'm doing right now is I'm just tracing the outline of one of the pi wedges, and this is a pi wedge whose angle is 1 radian. Now notice that they labeled the arc length R. They did not label it S. And the reason that this diagram does that is because we're trying to emphasize that for 1 radian, the arc length equals R. And so we can simply label it R since it's the same length. All right, right next to that pi wedge, we have another pi wedge with also a degree, or I'm sorry, an angle of 1 radian. And so since this pi wedge has an angle of 1 radian, we put it right next to, and we put all these pi wedges next to each other, we can observe some very interesting things. First of all, let's look at what happens when we put 3 of these pi wedges together, and then we end up with this tiny little sliver here, which would make the full 180 degrees, or half pi. Well, look at how many pi wedges fit into that 180 degree piece, and you'll count it. It's 3 full pi wedges and a little portion that happens to be equal to 0.14. And so we have 3.14 pi wedges, or we have pi. And by the way, this is not where we get the name for pie from, just because of the pies that you eat. But it is something kind of helpful that we can maybe associate. We can associate it in our memories with a nice appetizing concept. Because, sure enough, in half a pie, and I'm talking now about the pies that you can eat, and let's imagine this circle that I'm circling here. Let's imagine that as a nice edible pie. Well, in half a pie, there are pi radians. In half a pi, that is half a PIE, there are pi radians, that is PI radians. Okay, now let's continue looking at this pi, and we go all the way around, and we have a full pi, PIE. And in a full pi, PIE, there are 2 pi, PI radians. Okay, that's kind of interesting, right? And we're going to see just how logical and beautiful this is and how much it makes sense. Okay, so for now, since we're really just dealing with general concepts, for now the important thing to understand is that in a full circle there are 2 pi radians, and therefore we can write this equivalence. 360 degrees equals 2 pi radians. And we'll see on the next screen that this will help us to convert radians to degrees and vice versa. But for now, make sure you understand that 360 degrees, which is a full circle, or a full PIE if you like, equals 2 pi radians. And we can clearly see by looking at this diagram that there are 2 pi radians in this full circle. If you do on your calculators, if you multiply pi by 2, you'll get something like 6.28, 6.29, around there. Well, that is exactly how many different little pi wedges we have within this big pi, or this big full circle, if you like. All right. Now, what else can we tell from this diagram? Besides the fact that there are 2 pi radians in 360 degrees, we can also tell a few other things. Now, first I want to mention something, that circumference over diameter equals pi. This is not something that we get off the graph. This is just a basic fact. And I'm often surprised by how few students, when they get to pre-calculus, how few students actually know where pi comes from. And for those of you who don't know or don't remember, you may be interested in this fact that pi is simply, by definition, circumference over diameter. So any circle in the entire world, no matter how big or small, if you measure that circle's circumference and divide by its diameter, you will always end up with the number pi, 3.14159, etc. So circumference over diameter equals pi. Now, if that's true, if circumference over diameter equals pi, well, then it's also true that circumference over radius equals 2 pi. Why? Because the diameter is 2r, and so all we're doing is multiplying this equation, both sides, by 2, and we end up with circumference over radius equals 2 pi. And that brings us to a final step, which is circumference equals 2 pi r. Now, you may remember from geometry that the formula for circumference is 2 pi r, but now we've just derived it. This is how we get the formula for circumference of 2 pi r. It basically comes from the definition of pi as circumference over diameter. So if circumference is 2 pi r, well, let's look at what we have here at this circle. Notice how the arc lengths are labeled r because each arc length is equal to the radius. And if we count the r's going around, notice how the number of r's in this circumference is 2 pi. So if we want to measure this circumference, we'll notice that it's equal to 2 pi r. And that is a visual confirmation of the formula that we just derived from the definition of pi. All right, so the main thing on the screen is to realize how arc length and radius and radians are all interrelated, and also to realize how pi, as in pi, is related to pi as in PIE. Of course, if that image doesn't help you, don't worry about it. You certainly don't need it. And also, it has nothing to do with the etymology of pi, either the eating pi or the number pi. But the main thing for the screen is have this diagram etched in your minds. Know that the circumference is 2 pi r. Count up the little r's to prove that to yourself. Know also that there are 2 pi radians in a full circle of 360 degrees. And when you're confident about all those concepts, then go on to the next screen. Now here are some common radian angles, and it's pretty clear where they come from. You know, pi over 6, if you divide this, okay, we have a pi here. I'm talking about PIE, of course. If we divide this pi, and we only look at half of it, and then we further divide that half, well, I can see that pi over 6, where I'm talking about the number pi over 6 is really just 180 degrees divided by 6, and that equals 30 degrees. So pi over 6 is a common angle that you should memorize because pi over 6 is 30 degrees. Pi over 4 is another common angle. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees. Pi over 2 is 90 degrees. Pi is 180 degrees. And 2 pi, as we've proven to ourselves on the last screen, 2 pi is 360 degrees. Now these common angles, these common radian angles, you're going to be using very frequently. So definitely write them down, but also study them, because whenever you see pi over 4 or any multiple of it, like 5 pi over 4 or 3 pi over 4 or 7 pi over 4, whenever you see pi over 4 or any multiple, you should be thinking, 45 degrees or some multiple thereof. You have to be able to do the equivalence just immediately in your mind. Now, I understand you may not be at that point yet, and that's fine, but just realize that you have to be, and you will need to know these common radian angles like the back of your hand. How to convert angles? Well, if 360 degrees equals 2 pi radians, which we've already established, well then 180 degrees equals pi radians. All you do is divide both sides of this equation here that I'm circling now with a mouse arrow, divide both sides of that by 2, and you end up with 180 degrees equals pi radians. And if that's true, then 1 degree equals pi over 180 radians. And all we did there, see, is we looked at this and divided both sides by 180, and we got 1 degree equals pi over 180 radians. And 1 radian equals 180 degrees over pi. So for that formula, we just looked at this equation here that I'm circling now with the mouse arrow, and we divided each side by pi. And so 1 radian equals 180 degrees over pi. Now, if we want to convert, then based on what we just proved, we can say this: to convert degrees to radians, you multiply the degrees, whatever those degrees are. You say you get an angle in degrees, you just multiply it by pi over 180, and then you'll get that angle in radians. And to convert radians to degrees, you multiply by 180 degrees over pi. So you get some angle in radians, you want to convert it to degrees, multiply that angle by 180 degrees over pi, and you have your answer. So example, convert 135 degrees to radians. Pause the video, do that on your own, and then resume when you have an answer. The answer is 3 pi over 4 radians. 3 pi over 4 radians, because I simply multiplied 135 degrees by pi over 180, and I end up with 3 pi over 4 radians. Now you could have written this as 0.75 pi, that's fine too, but it should be equivalent. Another example, convert 2 radians to degrees. Pause the video, do that on your own, and then resume when you have an answer. And 2 radians is 114.59 degrees, because what I did is I just multiplied 2 by 180 degrees over pi, and I got 114.59 degrees. Here's the classwork, page 291. Write those numbers down, and see you in class.